Hi everybody. I wanted to work an example of an independent and a dependent T in R with data screening, kind of updated from my example from last year with some new things that we've infused into my graduate statistics course, and so just some new ideas on how to run these types of tests. So the first thing I'm going to do is make up some example data, so there's no data to import. You can find this R script on our website, hopefully very soon. And what it's going to do is it's going to create us a random normal distribution with different means. So in our fake study here, we have two measures of some type of variable and then a factor variable, so a group, where people are either learning things from me through YouTube or learning things in my class. And so we can pretend these measures are exam scores. So time 1 exam, time 2 exam. And we can look and see if there are differences in these scores based on where they learned the class. Now in a perfect world, this actually would be mixed ANOVA, but since we're talking about t-tests, we're just gonna run a couple of example t-tests. But generally you don't have data that is just one t-test, but we'll talk about how you screen it if you do and if you don't. Okay. Now, since I'm making this data from a random normal distribution, you will have different numbers than me. So it'll allow you to kind of follow along, but be aware that you're not going to have exactly the same scores. There'll be decimal points kind of different. So what we're going to do is create these these distributions of random scores based on with means of 10, 12, 15, and 20. I'm going to put all that together into one giant data set that we're going to call example data and convert that to a data frame. That's the type of thing that we're used to working with. Now this data frame has time 1 variable and time 2 variable and our grouping variable. However, our grouping variable doesn't have labels, and everything gets much easier if you include labels. You also cannot use ggplot without labels. So we're going to factor that. So remember, the factor command works by putting the name of the variable you want to factor. So it's the group column in example data. You have to put in the levels that exist already in the data. So if I look at the data, group 1, group 2, so the 1s and 2s, which is where this came from. And this is probably conceptually the hardest thing I think students have at the beginning, is that they always want to write 1 and 2 here. Sometimes it might be 0 and 4 because your research group you're working with is weird, and sometimes they might already be words, you just want to spell them differently. So this level thing has to be what is already in the data set, or you will wipe that column out. Okay. The labels here are whatever you want to call them in the same order. Okay. So I just made up some group labels for this data. It's totally just generated data at the moment. So let's work through some data screening first. So let's see if there's any issues with the data. So I'm going to look at accuracy and take a summary of the data set. So I already know it's factored well. And let's say that I know the maximum score or the minimum score should be 10. So anything below a 10 is just a typo, or we're going to exclude those students because they just couldn't even take the test, or we just know that for some reason those scores are incorrect. Okay. And this is just an example of how to deal with data that is in the wrong range. So we're still kind of doing accuracy here. So I'm going to say, okay, anything in measure 1 that's less than 10, we're going to make that NA. And so I know measure 1 has some scores that are less than 10 because the minimum here is 3. So let's just say I know that I curved everyone's test and these scores are typos. So we're just going to get rid of them. The way we do that is by first pulling the column we're interested in. So data set $ column name. That makes it one vector of data. And since I'm using a vector of data, in their square brackets here, I do not have to have a comma. Because remember, vectors are one column, so you don't use the row, comma, columns idea. Okay. Then I'm going to tell you the rule. So anything less than 10 is going to be equal to NA. So what this code does, and if you want to see this more in action, you can watch the data screening video, is it just eliminates all of the scores less than 10. Now if I run my summary again, I'll see that I have some NAs. But now measure 1 is not less than 10, which is good. Now measure 2, we'll let them fail if they failed, but measure 1 we didn't. Okay. Next thing I want to do, let's say I've checked all of my accuracy data points, so I know that my data is now accurate, the min and max are correct, and the factor variables are factored. I can calculate a percent missing. So percent miss, this little function that I've written, just allows me to use this in the apply function really pretty easily. It just calculates the number of missing values, so it sums up the missing values, and is divided by the total number of values. And this is in percent, hence the name of the function. So we're going to multiply by 100. And I've changed this a little bit after thinking about it. So you'll see my older videos, I usually do columns first, but now I'm really interested in thinking about this as what we joke around a lot in our lab is that participants are dumb. What we really mean is that they have different motivations and different goals for taking our surveys. And if we're using our intro to psych pool, maybe they're just bored and they're clicking through and they just quit in the middle. And I don't really want to use that data because they didn't finish my study. So this would be the same as if your computer kind of blew up in the middle of a survey if you were doing a traditional lab study. So I want to first look at the data by participant and really see how it's missing across participants. So this is a way to sort of exclude people who didn't complete your study or didn't do enough of the study to really be counted in the study. So we're going to calculate the percent missing for every person by using the apply function. The way the apply function works is that you use the name of the data set, 1 or 2 here, 1 for rows, 2 for columns, and then you type the name of the function. So I could calculate an average score by row by doing mean here, but I really just want to know how much data is missing by row. I'm saving that here as missing, so I don't get 100 rows of scores to look through. And then my table I just do here to see how it's missing. So we have 29 folks, and like I said, if you run this along with me, you'll have a slightly different score because of the randomization. So 29 folks that are missing a third of the data because we excluded it because it was too low. So we're going to exclude people who are missing too much data, which is pretty much everybody at this point who is missing any data points. And so I'm going to call those replace people in case I could replace folks. Now in general for missing data in t-tests and ANOVAs, you really don't get to do a whole lot of replacement or using a function like mice because you just don't have enough columns to really justify that sort of action because the participants are missing a lot of data. And if you're talking about a one-way ANOVA, if they're missing the DV, you wouldn't want to replace them at all because then you're making up data points. So here we're just going to exclude them basically if they're missing because there's just too much missing data. 5% is a good rule. I pulled that from Tabachnik and Fidel. And so I'm subsetting this into 2 different groups. So replace people, so that's our 71 people that aren't missing any data, and our don't people, these are people we wouldn't want to replace. Now I could combine those back together at the end and use them for one hypothesis versus another, but in this case I'm just going to exclude them because they don't have a complete data set. Okay. The reason that I create both halves is if I do want to combine them, I have both halves to do it later. Plus it makes it really obvious to see these scores, like over here, where there's 29 missing and 71 that aren't. The next thing we'll do is calculate by column. And at the moment we don't have any missing data at this point. So I'm calculating on this data set. And if I had columns that I could replace, I could use the mice library to calculate the replacement scores, but I'd have to split by column as well. So if you want to see an example where we split by rows and columns and replace and put them back together, there's some data screening videos, also some EFA videos that talk about like in very large data sets where this is more applicable. Okay. But right now, I don't have any data to replace after I excluded people who've had too much missing data, and so I'm just going to create a no missing data set from my replaced people. Now I'm creating a lot of like separate data sets here, but unless you're working with just very, very large data sets, this shouldn't cause you any computer problems because R can sort of handle holding a bunch of these different ones in memory. But if you wanted to, it helps me to see the steps that I've taken. And so that's one reason why I suggest making a lot of these data sets. All right. So one problem that we'll run into when we talk about ANOVAs is that there's literally only one dependent variable column. Now, if you're talking about repeated measures ANOVA, you can screen the data by before you melt it into one column and talk about and use it in wide format. But if we're talking about just like between subjects ANOVA, there's only one column. And if you're just doing one test, you can't use Mahalanobis. Mahalanobis requires there be two columns because it uses the covariance function, and you can't covary scores with one number. So instead, what you can do is look at using z-scores. So the rule for z-scores is that they should be less than 3, so 3 standard deviations away from the mean, which makes it p less than 0.001, or it's very close to that criterion. So it's still that 001 rule for data screening. So we're going to create z-scores by using the scale function, and I did this on just one of my measures. In reality, I'd want to do it on both, but we're sort of pretending at the moment that I only have one variable. I could take a summary of that. Now in my summary, I can see based on the min here and the max that I don't have any that are greater than 3. So I could just move on. But I like to use the same code over and over again and edit it for my purposes. So I've created this no outline where it would subset for me and take out any z-scores that are bad if I were to say run this again and get a different set of scores. So I'm going to subset my no missing data, and I'm going to use the absolute value of z. This makes it so that you only have to do this once, and you don't have to say anything greater than 3 or less than -3. So this just makes it a little easier for you, but the absolute value is important. Otherwise, you'll only get chop off the top and not the bottom too. So anything that is less than or equal to an absolute value of 3. Now, in our case, we have some repeated measures data, or if I have multiple hypotheses and I want to screen everything at once instead of screening one at a time. Both directions are valid, but we've kind of talked to my class about screening everything at once, because then we're making sure that participants' data is, we're accounting for the non-independence of it. So if you have repeated measures data, columns are no longer independent from each other, and so we have to account for that fact when we're talking about outliers, and that's where this covariance thing in Mahalanobis becomes important. Okay. If you're going to use the Mahalanobis function, remember you have to drop categorical columns. So that's what this is here, this -1. And I'm pretending to do this on the no missing data set. So you would do one or the other. You would not, generally you don't do both z-scores and Mahalanobis. Some people do. I tend to think about it as if they're an outlier across the entire data set, that's a problem. But on one individual measure, maybe not. That's just a theory choice. It kind of depends on what your do what your advisor wants. That's always my #1 rule if you're a student, or kind of what does your field do, or what do you feel is appropriate, because both ways of looking at outliers are accepted. Okay. So if I'm going to do Mahalanobis instead, it's the name of the data set, dropping any categorical columns. Col means the name of the data set, again dropping the categoricals. I have na.rm equals true out here just in case I had put my NAs back in the data set. At the moment I don't have any, but that's okay. It won't hurt me to include this. And then covariance of that data set. So the data set stays the same across all 3. And then use pairwise complete.obs, that'll handle any NAs. So let's create those Mahalanobis scores. Now Mahalanobis is not quite as easy to work with because it does not have one cutoff score criterion. It depends on the size of the data set. So we're going to create this here, and I think what I had done before in my class was talk about this as 1 minus the criterion, so you can remember what you did. And so we're using 1 minus 0.001 because we're using p less than 0.01 as our cutoff score. Because we want scores to be very weird before we delete them. So p less than 0.05 seems a bit too liberal. We're going to use 001. Okay. And then to create this cutoff score, we use the degrees of freedom as the number of columns used, so the number of variables used for Mahalanobis. So in call to count the number of columns, and then you match here to here. Right. So that's going to create us a cutoff score. If you want to write this up, I'm going to output the cutoff score. It's 13.82, which is for 2 degrees of freedom. Does that give us any outliers, though? So we're going to take a summary of our Mahalanobis scores and see which ones are less than the cutoff. And so we don't have any multivariate outliers in this data set. But again, I'm going to create a no-out data set where I exclude any multivariate outliers, very similar to what I did out here. And so I know if I run it again and I have a different data set, it would at least exclude them. Now, generally we talk about additivity, which is not having multicollinearity or singularity in our data set, but it actually does not apply in t-tests. We expect repeated measures to be correlated, and usually fairly highly. The only time you'll have trouble is if they're perfectly correlated, but then nothing will run. It'll blow up. So generally additivity here doesn't apply. Now I'm going to set up my assumptions. Oops, sorry. Scroll up a little bit here. And we're just going to set up a random variable to test our assumptions against using a random chi-square distribution. And it's chi-square because residuals are chi-square distributed. I'm going to use the number of rows in my no-out data set, and then 7. 7 is just a number that has worked for me a million times. You could put 4, you could put 386. As long as you aren't using like 1 or 2, you need something a little higher to get enough variance here. Okay. And so now, really, our data is going to be a little different here because this is random. We're going to create a fake regression to test our data against random. So random is approximated by dot. Dot means give me all rows and columns. And I can use categorical variables here. And we're going to use our no-out data set. Okay. And if you want to hear more about the reason why you would do this, you should watch our data screening lecture. Okay. We're going to create our standardized residuals, or these are our studentized residuals with the rstudent function on the saved fake regression. And we're going to create our fitted variables by using the fitted.values function piece in our fake regression, but we're going to scale those, so we're going to make them z-scores. They're easier to interpret when they're scaled, okay, because then they're centered over 0, so it makes the rules fairly consistent across this next section. If I want to look at the normality for my standardized residuals, I see this is okay. It's actually not great because it is centered over 0 and mostly between 2 and 2. Maybe a little bit of a tail out here in this picture, so over here. If I feel kind of like, ooh, I don't know, try rerunning your random setup and look at it again. And these will change slightly because we are predicting a random variable, but if it is consistently skewed, that's when you know that it's skewed. So we have a consistent small tail out here. And that's probably because we cut off the bottom of one of our measures and not the other. So that's probably where that's coming from. So I would say this is a little skewed. Because I would say it's a little skewed, which measure is it? So I'm going to run my histograms for each individual measure, and I can do that here kind of easily because I only have 2. If I had 40, this would be kind of tedious. It looks like measure 1 is actually a uniform distribution, so it's fairly blocky. So that might be part of the skew problem. And measure 2 is slightly skewed towards the bottom. So we have 2 slightly skewed distributions. But remember, normality tends to be okay as long as you have at least 30 people, and we definitely do. If I want, I can use the moments library to calculate skew and kurtosis, but remember, you have to drop the categorical columns. So here I've done apply, so I want all columns, so I'm dropping categorical ones, so it'll freak out. 2 for columns here, and then calculate skewedness. So neither of these are really skewed. Okay, remember that 3 is the rule. And they're a little kurtotic, but not in a problematic way. Okay. Another thing you can do is calculate skew and kurtosis by group using tapply. Remember that tapply works with categorical variables. So we've got dv here, and then IV, so by group, and then the function you want to use. And if I look at this by group, I can tell that the YouTube group for measure 1 is a little more skewed than the class group, and it actually is kurtotic more than the class group. And that's just one thing we can look at. I have at least 30 people, so the sampling distributions should be normal due to the central limit theorem, but just some different ways that you can examine your data set. For linearity, we're going to use the QQ norm function, so it'll create us a QQ plot based on the normal distribution. And I'm going to add a line from 0 to 1, so I have something to kind of judge against. And mostly you want to look at between 2 and 2, and I'd say it's pretty good here between 1 and 1, but starts to bounce off here at 2. So maybe a slight cubic distribution. And so I might consider, if I were using linear or regression analysis, trying some different polynomial functions, so like a trend analysis. But in general, it looks kind of okay. It is always harder to predict variables at the end. The end of the distributions. If I want to look at homogeneity and homoscedasticity, I can create a plot of my fitted variables to my standardized scores. And this plot looks a little funny because there's nothing here in the middle. But we can create some lines to judge this on. So this plot looks actually really pretty bad. Let's try running the random thing again, see if we get the same bad picture. Okay. That won't change skew and kurtosis. Those are going to stay the same because those are not dependent on the random variable, but this picture is. Okay. This time I didn't get that split. So I would run this probably a couple times to make sure that that was just, you know, a function of a little bit of randomness. Now this picture, so for homogeneity, we want it to be spread evenly around 0. That's why we drew the 0 line here. So from 2 to 2, it's actually pretty good. This way, not as good. So it's -1 to 3. And Bargy is probably okay because most of the data is kind of between 2 and 2. So it's not perfect, but it's not 1 to 4. For homogeneity, we don't want it to make this sort of triangle picture. So this might be a little bit, homoscedasticity might be a little heteroscedastic because it kind of makes this triangle-ish picture. So there's data missing up here. But before I would say, oh no, abandon the linear model, I'd probably run it again. And so that's the nice thing about having this code is that you can run it a couple, 3, 4 times. And it still is a little more homogeneic. There's one little dot up here, but it's still kind of making this triangle picture. Okay. So heteroscedasticity might be a problem. All right, so continue with t. You know, I might actually consider trying this as maybe a non-parametric t-test, but for purposes of talking about regular independent t, let's keep going. The first thing I'm going to do is turn scientific notation off. It makes it easier to read our p-values. We're going to use t.test. So t.test, it's dv tilde iv. So, and that's true anytime you see the tilde, the y is on the left, x is on the right. Data equals whatever data set you're using. var.equals equals true. I could turn this off if I wanted a Welch correction for homogeneity problems, but we said homogeneity is kind of okay. Paired equals false because this is independent. So what we find, because I made up fake data that's very different, is that it's significant. So we would write that as t with 69 degrees of freedom equals 7.57. P is less than 0.001. And you can see it's just a little easier to read it. You can tell it's significant versus scientific notation. It gives me a % confidence interval on the mean difference, but then also my means here. But let's say instead of looking at just this, I want to add effect size. So this is significant, but is it practically important? What we can do is run tapply to get the mean, the standard deviation, and then n. So how many people are in each group. Can also get standard error here. I'm just going to output those all at once. So here's our means. So those means should match these means, and they do. Here's standard deviation, the number of people in each group. So this is a little imbalanced in a bad way. And then the standard error. Now, what I mean by a bad way is it's almost double the size. That will always can bias a t-test. So we want to be careful with this kind of group size difference, and it may be wise to do a correction on this, so a Welch correction, but it would be better if we had 30 in each group and they were a little more balanced. And so what you can do is now we can run the second t-test here. Right? It is also significant, so a big difference here, 15.78. And I can run my second set of means. And so there's almost a 9-point difference between the group learning just on YouTube, sorry YouTube, and the group in my class where I'm waving my arms around in class. For effect size, we can use Cohen's d, and I have this fsize.r script. It's on our website, or if you're in my class on Blackboard, and you would need to run the entire thing. Okay. So I'm going to run the entire thing, and why? So that I get all the functions that we're going to use here. So once it's done running, you'll have a whole bunch of new functions over here for calculating effect size. So for regular Cohen's d, where it's mean minus mean over pooled standard deviation, I can use d.independent t. Now, these mean scores will not match the mean scores that I just calculated because it's randomized every time. I just typed these up on the first run just to show you what it looks like. So in reality, what I can do is run my means and standard deviations and then type them into this sort of formula. So I could do 11.47, that stayed pretty close. My standard deviation changed a little bit, so I could do 1.37. This time in is 21. We've got 14.89, 1.86 with 50 participants. And alpha here is whatever we set type 1 error at, so 0.05. K is 2, so that's decimals. We'll run that. Our t values should match, and they do. But our d score is almost 2. So this is a very large effect. So the difference between these two means is very large. Okay. I won't bore you with typing in the second ones, but let's say I run that second one. Also a very large effect. So we get 3.86. So really two very big effects because I made up the data that way. If I wanted to create a chart of this, I could use ggplot. I've written some kind of cleanup code because the fact that ggplot plots are automatically gray with all these grid lines makes me nuts. So this code here is just, it's also in our data graphs code. It's just a way to clean up the plots and make them a lot more readable. So I'm going to save that so I can use it a couple of times. Then we're going to create a bar chart of just the first one. So data set, aesthetic is IV, DV. And then to that, I'm going to add a bunch of stuff, which is explained in a lot more detail in the graphs lectures. But we're going to create those bars on the mean. I'm going to create a confidence interval around the mean of the bars. Add a X label that's better than just the name of the variable. Add a Y label. Make sure our X and Y labels are appropriate. So here, let me run this up to here. Show you what scale X discrete does. Okay. What didn't it like there? Oops. Helps if you run and create the bar chart first. Boop. There we go. And so I haven't added the theme coding to it, so here's how it looks without adding any extra thing to it. And then learning group, YouTube, and class. It might be better if we just gave it a little bit more description, so that's what that's going to do. Here's something new that I don't talk about in my other videos, is chord Cartesian. That allows us to change the X and Y limits to maybe what the data set should have. Now, the data set does go higher than 20, but let's pretend that it's 20. That will change this from looking like a very huge difference to being maybe a more appropriate representation of the difference. So don't distort the y-axis. And then our cleanup code, which when we clean it up, it's much, much easier to read. And so we have our average confidence from 0 to 20 and watch YouTube. Now that looks really huge, but when you hit zoom to actually look at the graph in sort of full format, those font sizes are a little more normal, but they're much easier to read when you cut and paste them into Word or whatever program you're using. So you might be using, I'm never sure if it's LaTeX, I've heard it 6 different ways, but you can link those two together to import graphs from ggplot, and so that'll make it a little bit cleaner to see. All right, the last part of this, let's talk about dependency. So with dependency, our data set is in wide format. You can actually run a dependency in wide format, but I don't want my students to do that because we're going to work on repeated measures ANOVAs, which have to be in long format, and so it's just much easier if we talk about doing everything in long format. So we're going to use a reshape function to take our data from wide to long. And what I'm going to do is, it's the name of the data set. Any variables you don't want to change, so this might be all of your measurement times if you had created average scores. Your variables you do want to mount. Okay. Now, when you do that, so I've got a long note out here, it stacks the data sets for you. But here's the problem. It labels them really helpful labels like variable and value. So I'm going to use the call names function to give those things names that make sense. So we're measuring time and I guess confidence here in our skills. We're going to use t.test again. So it's dv tilde iv. Data set's long, no out. var.equal actually does nothing for a dependent t, but it doesn't hurt to leave it in, so you don't forget it an independent t. And then we're switching from parrot equals false to parrot equals true. Oops, I'm just running the letter O. Let's try that again. There we go. So we have a very big difference because, like I said, made up data. Here's the confidence interval on the difference, and here's the mean difference score. So they're scoring about 3 points difference in confidence, which across time, which is a significant difference. I can get the means for each time point using tapply in the same way I did earlier, now that it's in long format. So I can get my means and standard errors for each time. So that 3 point difference is because the first time they are feeling less confident than the second time. And I can use those scores to calculate D averages. So Cohen's D with so it's a new form of Cohen's D. It's the first place I saw it really was suggested by Jeff Cumming in his book Understanding New Statistics, and it is supposed to be a more representative D, whereas D differences tends to overestimate a effect size for D. But either way, this formula is calculated by doing mean 1 minus mean 2 over an average standard deviation on the bottom, which is more like independent t. And so it doesn't inflate it based on standard deviation of the difference scores. So I would fill in mean 1, SD1, mean 2, SD2, and I would use the new numbers here if I felt like changing it, which it's close enough for right now. And so it is a large effect, 0.9. Okay. Now, if you note in my code here, it says I'm not reporting T and P. Those are used to calculate the non-central confidence interval for D in this particular script, but they're not shown to you, so you're not tempted to report them because they would not be correct. They would not be dependent T, it would be independent T. Let's instead say, I want to do traditional dependent T effect size, so D differences, where the effect size is mean 1 minus mean 2 over standard deviation of the difference scores, because that actually matches the test statistic. What you have to first do is create yourself some differences between those. So we're going to just subtract measure 1 minus measure 2. Notice here that I switched from long format back to wide, and by using the wide data set, it's easier to subtract. Create a mean of that difference score, so that should match our t-test, an SD of the difference score, and I can also calculate the standard error of the differences. So our t value is the mean differences divided by standard error of the differences. Dependent t diff is calculated here, this small little function with a mean diff, SD diff, and n. Okay. And so here I got 0.97. Now they're not that different here because they're uncorrelated. and the standard deviation of the different scores and the average standard deviation are approximately the same. There are times with very, like if you have different scores that are, like everyone is getting approximately the same difference score, it will decrease the standard deviation of the differences and really inflate the effect size. So they can be very different. And my suggestion to just kind of researchers in general is tell people which formula you're using. So, there's reasons for one over the other. I see them both ways as appropriate. Just telling people which one you're doing is important. All right, if we want to make a graph here, it's actually the same, pretty much the same graph as above, like the code for it. We're using the long data set though. Time and confidence as our IV comma DV, or X comma Y. We are changing Y to confidence and X to time. And I'm going to use core Cartesian again to chop off the top and use my cleanup code. So now I have a graph of time 1 rating and time 2 rating. So hopefully students are getting a lot more confident in their skills. And this sort of ignores the class that they're in. Okay. And in a perfect world, we'd actually run this as a mixed ANOVA, but this is how you would run independent and dependent T, complete with effect sizes and graphs. Let's talk a little bit about G-power. So if I wanted to calculate power for these, let's talk about independent T first. So under test family, I'd pick t-test. Under statistical test, I would pick, for independent T, and sorry I can't make this font any bigger, it's differences between two independent means, two groups. I'm going to use a two-tailed test, and we would input one of our effect sizes. So let me go back up here, look at one of the t-test effect sizes here. It's 1.97, so really large. Alpha is 0.05, power is 0.8, that's industry standard. And our allocation ratio here, so we have 21 in one group and 50 in the other. So I would just divide those out, say 0.42. You can actually do this either way. And then I hit calculate. Because of the super large effect size, it says we only need 12 people. Okay. Usually you can switch the allocation ratio and get approximately the same numbers. Right, so it just changes the sample size for each group. Every once in a while it changes just a touch if they're very unequal. And in this case they're about half, so they're pretty unequal. If I wanted to do dependent T, so let's come down here to dependent T averages. Since there are some reports that it is a better representation of a population difference. So 0.9. Under test family we pick t-test. Means differences between two dependent means, matched pairs. It's a two-tailed test. Effect size is 0.90, 0.05, 0.80, and I also only need 12 people. Now we can try this with both effect sizes, so we could see the range of people that we would need. So somewhere between 11 and 12. It didn't make that big of a difference. Okay. So that's power, graphs, t-tests, and effect size. And so from there you should be able to write that sort of thing up. Really, most people aren't doing just like one t-test. You're doing either several, or this might help you with the understanding of a follow-up for post-hocs in ANOVAs.